Hello, this is Dr. Baxley. This is part 4 of the Chapter 7 lecture video series. In this video, we're going to talk more about how electrons are weird. More specifically, we're going to talk about something called quantum mechanics, or the physics of really small things. Now, at the end of the last video, we were faced with some problems. We still didn't really know whether electrons were waves or particles, although they act like both in different experiments. We also didn't really know what was up with Bohr's model. He had this great model. Balmer and Rydberg had this great equation, but the equation didn't predict the behavior or the emission spectra of any element other than hydrogen. It left out 117. It's not a very good formula. It really bothered chemists and physicists to not have a great model for how electrons behaved and why these emission spectra occurred. But Bohr's model seemed to be the best thing they had going for them. Until Heisenberg came along. Not this Heisenberg from Breaking Bad, but this Heisenberg. Heisenberg was a student of Bohr, and as any good student did, he questioned his PhD advisor. And Heisenberg said, wait a minute, electrons are too small. They're moving too fast. You can't determine the momentum and position of an electron moving at the same time. Maybe one, maybe the other, but not exactly both. And so Heisenberg came up with an equation. It was delta x times delta mv has to be greater than or equal to Planck's constant again, divided by 4 pi. Strange equation. We're not actually going to use it, except for a couple of examples. The delta x is the uncertainty in position. Heisenberg said that the position couldn't be determined along with the momentum, and so delta x is the uncertainty in where something is. The delta mv term is the uncertainty in momentum, which is mass times velocity. That's the direction it's moving in. So that's what Heisenberg was saying. We don't know direction and position at the same time. This was kind of an in-your-face to Bohr, his advisor, because Bohr's model was pretty much knowing the location, the orbit, and the direction, flying around the electron in the orbit, at the same time. Heisenberg said, Let's digress for a little bit and talk about some practical things. If all particles acted like waves, like de Broglie said, why don't baseballs act like waves? Well, we can take de Broglie's equation and see what would happen for a baseball to act like a wave and make pretty patterns like peacock feathers in sunlight. If a baseball was moving at 1 meter per second, the slits in a diffraction grating is just a piece of material with lots of thin little grooves or spaces in it. The baseball would need slits that were 4 times 10 to the minus 33 meters apart from each other. That's impossibly thin. The best we can do is about 10 to the minus 7 meters in terms of spacing. For 10 to the minus 5 meter spacing, which is pretty achievable, the ball would have to move at a really slow speed, 4 times 10 to the minus 28th meters per second. It would take an incredibly long time for a baseball to move 1 whole meter to show a diffraction pattern like light would. It turns out the Earth is only 1.5 times 10 to the 17th seconds old, so we would have to wait longer than the age of the Earth by a factor of 10 to the 11th in order to see a baseball rainbow. It's just not going to happen. Let's take baseballs and go one step further and talk about Heisenberg's uncertainty equation. We can look at the speed of an electron and the mass of an electron and calculate the delta x, or the uncertainty in position. We can do the same for a baseball. Here's Clayton Kershaw. One of his slower pitches is going to be 43.9 meters per second. That's like 88 miles an hour. We know the baseball's mass in kilograms. We can also calculate its delta x. Now it turns out for an electron moving at that speed with that mass, the delta x is 0.15 nanometers, which sounds like we know its position pretty well, 0.15 nanometers. The problem is that the radius of an atom, even a small atom like hydrogen, is about 0.15 nanometers. So the delta x is really not knowing the location of an electron on the whole thing that it's supposed to belong to. It's like saying we know your location on Earth to be somewhere on Earth. It just isn't very helpful. Now a baseball, because it's not moving very fast compared to an electron, and it's huge and massive compared to an electron, its uncertainty in position is 1.1 times 10 to the minus 25th of a nanometer. We know exactly where the baseball is. There's almost no uncertainty in its position. That's because it's so big and moves so slow compared to really small particles. To summarize what we've learned in the mid part of Chapter 7, electrons can act like waves or particles, depending on the experiment. And we'll use those two ideas, that electrons can be waves or particles, later on in the course. Heisenberg's uncertainty principle is really important, but it's only a problem with really, really tiny particles and not with baseballs. I told you in the first video that I would try to give you some analogies. Well, here's my best analogy for Heisenberg's uncertainty principle. If you look at this picture of cars on a freeway, we can pretty much tell the position of the cars relative to each other. So position is good, but do we know momentum? Do we know how fast the cars are going? Do we even know if the cars are moving? This could be LA traffic. Those cars could be stopped. The cars in the foreground, in the front, they could be moving backwards for all we know. We're pretty sure these cars are either stopped or moving forwards because they don't have backup lights on. So here's an example of a picture where we can determine position, but not direction or speed. Here's another picture of traffic. In this particular case, we can determine the speed, or at least the direction of the vehicles, based on their headlights and taillights. But it's really difficult to determine the relative position of these cars. We don't know if they're in the same place, how far apart they are. It's really difficult to tell some positional information. Now, this is an analogy, so it's not a perfect example, but it kind of gives you an idea of what's going on with Heisenberg's uncertainty principle. We've seen these two experiments, where electrons can act like particles, or electrons can act like waves. Schrödinger came along. He said, I don't really care to decide whether electrons are particles or waves. I'm going to write equations where electrons act like particles and waves at the same time. And Schrödinger's equation leads to something called wave functions, and it gets this Greek letter psi. A wave function is simply a mathematical description of the shape of where the electrons are and how often the electron is going to be in a certain place. What this results in is the shape of what Schrödinger called an orbital and the electron density. We'll see some pictures in a moment to describe those terms. Now, Schrödinger was a really, really smart guy. Unfortunately, Schrödinger picked this term orbital, which sounds a lot like orbit. It's really easy to get the two confused. But Bohr's model, while easy to remember and makes nice pictures, isn't accurate at all, at least for anything other than hydrogen. So chemists typically use orbitals, which is just a place where electrons can be. Bohr's model didn't allow for electron-electron interactions. Electrons are negatively charged. So will two electrons next to each other attract each other or repel each other? Of course they repel each other because they're both negatively charged, so they'll try to bounce away. Bohr's model didn't account for that electron-electron repulsion, but Schrödinger's equation did, and Schrödinger's equation is much, much more successful. So here's some pictures of Schrödinger's orbitals. An orbital is just a place where electrons can be, and the shape of the orbital is sort of this vague outline that describes the outer boundary or outer limits of where electrons are likely to be. The electron density can be represented by this graph here shown in figure B, which is that electrons are much, much more likely to be found near the nucleus, and then it tails off rapidly as the electron gets further from the nucleus. You can kind of see that in the drawing of the orbital, where near the nucleus, the dots are much closer together, representing a much higher electron density. Further away from the nucleus, the electrons or dots fade and aren't nearly as dense. Here's an animation of what an electron orbital might look like. It shows the electrons moving all around. They're not moving around in a discrete pathway like Bohr's model. There's just some electrons flying all around in random places, and they're more likely to be found in the middle of the diagram and not quite so likely on the outside of the diagram. Now, if I could change this just a little bit, I would include a few more dots scattered outside to make it look less like a hard shell of electrons and more like a fading out into infinity of the dots. You've been waiting for it. Here's what one of Schrödinger's equations as a wave function looks like. This is not a simple equation like the Balmer-Rydberg equation. It's got second derivatives if you've had calculus. It's got space terms for where the electrons are. It's got energy terms. It's got potential energy terms. You don't need to know these equations. We are not going to use Schrödinger's equations to solve for where electrons should be around atoms in this class. In graduate school, I spent about 2 weeks working on a problem for a substance with 10 atoms, and we had to use Schrödinger's equation to calculate where those electrons were. Now, the wave functions from Schrödinger's equation do a number of things. One is they calculate what are called energy levels, how much energy a particular electron has. This is very similar to what Bohr's orbits were. We've already talked about how it calculates a space where the electrons are located. Those are called the orbitals. Each orbital for Schrödinger can hold 0, 1, or 2 electrons. Schrödinger's equation needs what are called quantum numbers. The first quantum number is given the symbol n. It's just like Bohr's n. It's a whole number. The larger value of n leads to a larger atom, more energy, and the electron can be further from the nucleus. Kind of like the orbits. But orbitals are not orbits. The second quantum number is called the azimuthal quantum number, or shape, and it's given L, or sometimes written as a lowercase l. If you're reading the text, you'll see that L is given as numbers, like 0, 1, 2, or 3. And those numbers describe the shapes of the orbitals. However, chemists typically use 4 different letters to describe shapes of orbitals. They use S, P, D, and F. If you're interested, the S stands for singular, the P stands for principal, the D stands for diffuse, and F stands for fundamental. Those are some old historic names for things about line shapes and spectra, like those emission spectra we looked at earlier. The third quantum number is the magnetic or orientation quantum number. This is given as m sub L, often written as m with a lowercase l. M sub L gives the 3D orientation of each orbital. Now some orbitals are spherical. They don't really have a 3D orientation. But other orbitals are kind of dumbbell shaped like this. And they do have a 3D orientation because there can be orbitals on 3 different XYZ axes. There can be one on the y-axis, one on the x-axis, and then one on the z-axis going away from and towards us. So the 3D orientation is given by that m sub L number. Again in the text, m sub L is given by numerical values like -1, 0, or +1. We're not going to worry about those at all in this class. The fourth quantum number for Schrödinger's equation is called the spin quantum number. And that's because electrons are thought to spin in 2 different ways. Electrons are particles after all. And so, just like any other particle, it could have a spin or a rotation. You'll see a diagram in the text that looks like this. The principal quantum numbers are the energy levels, or how much energy each electron has. Each energy level, then, can have sub-levels of energy. For n equals 1, there's only 1 sub-level, and there's 1 orbital here. And that means there can be 2 electrons in this particular orbital. In energy level equals 2, there can be a total of 4 different orbitals. 1 that has shape S, and 3 that have shape P. Since there are 4 orbitals total, there can be 8 electrons total in the second energy level. In the third energy level, there are 3 shapes of orbitals. There's S, and P, and D. And there's a total of 9 types of orbitals. And so there can be 18 electrons in the third energy level. Remember, we're not going to worry about the numbers assigned for m sub L or L. Some classes do that. We're just not going to do it. It's not that important. Most normal chemists I know, or most real chemists I know, they never sit around and talk about the m sub L level of an electron. But chemists do talk about S and P and D orbitals and energy levels. Those are quite important, so we're going to focus on those. In the very last video for Chapter 7, we're going to talk about orbitals and energy levels and all the different shapes, but that'll come next.